What if the emptiest parts of the universe weren't actually empty at all? Today, we're diving into a really mind-bending idea, one where the fundamental jitter of the quantum world might actually be the blueprint for space-time itself. All right, let's get into it.
You know, it all starts with this simple but pretty profound question. We think of the vacuum of space as the ultimate void, right? The very definition of emptiness. But what if it's not? What if, on the most fundamental level, that nothing is secretly humming with energy, constantly buzzing and jittering away?
So where does this wild idea come from? Well, it all comes down to a non-negotiable command from the universe itself. One of the absolute cornerstones of quantum mechanics, Heisenberg's famous uncertainty principle.
Now, you've probably heard of this principle, right? It's the one that says you can't know a particle's exact location and its exact speed at the very same time. The more you pin down one, the fuzzier the other one gets. But, and this is the part that's absolutely crucial for our story, that exact same rule applies to energy and time. You just can't know the exact energy of a system over an infinitely short period. Okay, so here's the math behind that rule, but don't worry, you really don't need to be a physicist to get the main idea here. See that triangle E symbol, delta E? That just means the uncertainty in energy. For that to be zero, for us to have perfect, absolute certainty about the energy, it would completely break this fundamental equation. In short, physics forbids a state of perfectly zero energy. The universe just demands a little bit of fuzziness. And this slide right here shows you the direct result of that cosmic law. On the left, you've got the impossible scenario, a perfectly still, zero energy, totally static vacuum. Heisenberg's principle says, nope, can't happen. Which means, on the right, you have what must be true, a dynamic vacuum. A space that is constantly, always fluctuating with some tiny, non-zero amount of energy. The universe literally demands this jitter.
Okay, so this leads us to the next logical question, right? If the void of space is forbidden from being perfectly still and empty, what is it doing instead? What does this constant required jitter actually, look like?
Well, this is where a really powerful idea called dynamic vacuum field theory, or DVFT for short, comes into the picture. And it doesn't just offer an answer, it paints a vivid picture of what this buzzing, energetic vacuum might actually look like on a physical level.
So DVFT basically proposes that the vacuum is this fundamental field that fills all of space. And it's not static, it's constantly pulsating at some base frequency. The theory describes this pulsation with things like amplitude, which you can think of as the height of its wave, and phase, which is kind of like its timing or rhythm. To make that a bit more intuitive, just imagine the entire universe is filled with this low, constant hum of a giant cosmic engine that can never ever be shut down. That hum is the vacuum field, always there, always oscillating, and providing the baseline energy that Heisenberg's principle absolutely requires.
Okay, so let's recap for a second. We've got two huge ideas on the table. Heisenberg's principle, which says the vacuum must have energy, and dynamic vacuum field theory, which says the vacuum is an energetic, pulsating field. Now here's where it gets really, really cool. How perfectly these two ideas just lock together. This table shows it perfectly. It's like a call and response. On one side, Heisenberg's principle demands a vacuum that can't be still. And what does DVFT provide? A pulsating field. HUP demands constant energy fluctuations. DVFT provides a coherent underlying jitter that satisfies that rule perfectly. HUP implies there's this deep link between a system's energy and its phase, and DVFT gives us a model where that phase is always evolving. It's just a perfect match. You could say HUP writes the law, and DVFT describes the reality that follows it. But look, this is so much more than just a neat theoretical fit that makes physicists happy. If this connection is right, it has absolutely massive implications for how our entire universe is built, from the tiniest particles to the largest cosmic structures. Because this constant jitter, it isn't just noise. It might be the very seed of gravity itself. And here it is. This is the big payoff. This unified theory suggests that the tiny, inescapable quantum jitters, required by the uncertainty principle, are the very seeds that grow into the force of gravity and the curvature of space-time. And before we even get to gravity, check this out. DVFT also helps explain another huge quantum mystery, wave-particle duality. In this model, a particle acts like a wave when the phase of that vacuum field is smooth and coherent, kind of like perfect ripples on a pond. And it acts like a particle when that phase gets scrambled or decoherent, when the ripples start crashing into each other. It gives us a real physical picture for a famously weird phenomenon.
Okay, now let's trace that chain reaction to gravity, step by step. Step 1, Heisenberg's principle guarantees the phase of the vacuum is always fluctuating. Step 2, these tiny fluctuations create differences or gradients in the phase from one point in space to another. Just think of it like subtle changes in the rhythm of that universal hum. Step 3, according to DVFT, it's these very differences that cause the fabric of spacetime to curve. And Step 4, what is spacetime curvature? It is gravity. There it is. The tiny quantum rule directly creates the grand cosmic force.
So, what does this all mean when we put it together? What's the final takeaway? Well, it offers a truly unified vision of reality, where the rules of the tiny microworld and the giant macroworld are deeply fundamentally connected.
You know, this quote from the source material just sums it up perfectly. The tiny, fuzzy rule of quantum uncertainty isn't just some weird quirk. It scales all the way up to become the grand, overarching pulsation of the entire vacuum of spacetime.
And this completely flips how we should think about the uncertainty principle. It's not some frustrating limit on what we can know. No, instead, it seems to be the fundamental engine of the cosmos, the very thing that guarantees reality is dynamic, energetic, and structured in the first place.
Which leaves us with a final, just staggering thought to ponder. Could it be that everything we see, from particles to planets to entire galaxies, is ultimately built upon a foundation of pure, irreducible, and absolutely necessary uncertainty?